and then we can get to the talk.
Okay. So should I just start, or?
All right. Yes. So we are online. So, hello everyone. Welcome to another Quantum Matter seminar. And it's my pleasure today to introduce Fiona Burnell from the University of Minnesota, and who's going to talk about quantum games for many-body physics. Fiona, please take it away. Thank you so much.
Yeah, thanks. So thanks for listening. And yeah, I'm going to tell you about some work that I did in collaboration with Veer Bulchandani and Shivaji Sandhi. Shivaji was at Princeton and I was at Oxford. Veer, I think, is still at Princeton. And yeah, the topic was quantum many-body games, essentially, and I'll explain to you what that means. So, and please feel free to stop me if anything's not clear, you have questions during the talk. It'll be more fun that way. So, all right, so this is, fundamentally a story about quantum entanglement and, how we might detect that in many-body systems. And so let me give you kind of a brief recap of quantum entanglement with the help of this animation from PhD Comics. Okay, so the idea is, I have two, I'm going to call them qubits. Okay, that's two-state quantum systems. Okay, and we know that it's possible to entangle them. And what does that mean? That means that, I have some measurements that I can do. Okay. And, in this case, I have two different measurements. We could think of that as measuring the spin along the x-axis or the z-axis. And the point is that the outcome of the measurement is perfectly correlated, meaning that if I measure x on both or z on both, that I always get the same answer, or, maybe perfectly anti-correlated. Think of a spin singlet. Okay. But if I look at the outcome of an individual measurement, okay, on either one of the qubits, that, it looks random, right? So, 50% of the time, it's like a coin toss, right? If I measure z, 50% of the time it's plus, 50% of the time it's minus, and similarly for x. But once I've measured z on one, I know what the outcome of a z on two would be. Okay. And, so the sort of reason that entanglement is so important and so interesting is that entanglement is, in some sense, it's really, kind of fundamentally what makes quantum systems different from classical systems. And in particular, it's a big part of what allows quantum systems to store information in a way that's, qualitatively different from classical systems. So, what do we mean by that? Well, let me remind you that probably the first time you heard about quantum entanglement was in your first class on quantum mechanics, and you probably heard about the EPR paradox from Einstein, Podolsky, and Rosen, right? And so, they basically did the following thought experiment. They said, suppose, and, which now has been done essentially as a real experiment in a BEC of rubidium atoms, okay, in this nice paper here. But, they basically said, imagine you have a bunch of particles, a large number of particles, and we're going to send half of them over here to A and half of them over here to B. And let's suppose that we're going to prepare these particles in a state where I have two non-commuting variables. They were thinking position and momentum, okay, but we could think about, spin in the x direction and spin in the z direction, okay. Such that, basically I have these perfect correlations between a particle on A and a particle on B, right? So I could imagine making a large number of kind of spin singlet pairs, right? And then, transporting one member of each pair over here to B and keeping the other one over here at A. Okay. And then, what they said is, basically now these things are separated and, now I could measure for example, all of the spins in the x direction at A, and then I would know, what would have been the outcome of the measurement of B. And, even though A and B could be space-like separated, I would know that outcome. And similarly, I could also simultaneously measure all of the z's at B and infer what the z's would have been at X. And so if you, kind of think about it, this also violates the Heisenberg uncertainty relation. Okay. And so they were sort of using this thought argument to argue that quantum mechanics was fundamentally incomplete. And, Einstein's favored resolution to this was what he called local hidden variables theories, where, it's just, we're just not aware of everything that's kind of controlling these quantum evolutions, but there should be some underlying probability distribution that, tells us about where these correlations come from and the outcomes of these these measurements. Okay. And I think that a really great insight was due to Bell, who basically pointed out that actually this was not a philosophical question, but a testable question. And he came up with these experiments known as Bell's inequalities, where you can basically show that a theory with a classical probability distribution will give a different outcome than the probability distribution that you get with quantum mechanics. Okay, and so you have some upper bound on the probabilities of certain combinations of events classically that quantum mechanics can exceed. Okay. And so this is a kind of little picture of that, right? So we have Alice and Bob, and in the middle we have a machine that's making entangled pairs, okay? And Alice and Bob are going to do measurements on their entangled pairs and calculate some features of the probability distribution of the entangled quantum wave function, and use those features to ask, could that probability distribution have come from an underlying, kind of classical distribution, which is which satisfies locality. And of course, this was what won the 2022, Nobel Prize in Physics, was for, kind of these generalized Bell tests and tests of entanglement, because I think, by this point, it's quite clear that local hidden variables theories are, empirically not consistent with the data. And there's been a number of tests, and okay, it's not a talk about these tests, but there's some really beautiful work that says that, this entanglement property of quantum mechanics, this strange collapse of the wave function at distance, and so on is all real. Okay, so with that preamble, let me, sort of give what I think is an interesting sort of set of questions, or, kind of many body perspective on these questions about entanglement. So we know that we have these beautiful empirical tests of entanglement. They're not easy to do, but they have been done, okay, and Bell inequalities. And, I think a modern perspective on entanglement is that the question is not so much, does entanglement exist at a fundamental level, but rather, if you have some kind of quantum process or experiment, does it have the kind of entanglement that you want to use as a resource as you work your way towards building, kind of an actual quantum computer, right? And so, we want to understand, how to, in particular, experimentally verify that we have entanglement in some system, right? And ideally in some system of many qubits. And so that's sort of one, context in which you might be interested in entanglement. Another context in which people certainly have been very interested in entanglement is that entanglement is also a very interesting diagnostic of phases of matter, actually. So that is to say that if you look at the ground states of, many kind of interesting quantum Hamiltonians, you can sort of diagnose them with characteristic patterns of entanglement, okay? So an example of this that's, of particular interest to the quantum information community is the Toric code or surface code, or more generally topologically ordered states. Okay, these ground states have characteristic entanglement patterns. And, it's worthy of note that, something that people have done, a few different groups have done, which I myself found highly amusing, is, to prepare, for example, these kind of topologically ordered states on your favorite quantum processor. So there's, papers by the Google group where they prepared Toric code states and Toric code states with defects in them. There's a paper by Quantinuum in collaboration with the Harvard groups, so Ashwin Vishwanath and Ruben Barisan and other people there, where they showed that they can actually prepare sort of more complicated topologically ordered states. And okay, so people can actually sort of start thinking about making these things on quantum processors. And, I think this kind of naturally leads to the question, well, wouldn't it be nice to have, a kind of interesting many-body test that, really kind of definitively shows entanglement in these kinds of systems, similar to a Bell test. And so that's the kind of question that I'll talk about today. Any questions so far? Okay, cool. All right. So this brings me to the topic of sort of quantum games as generalized Bell's inequalities. So, Bell's inequalities per se, or the CHSH inequality that you maybe first learn about in class, or that was tested experimentally, are, specifically for two qubit or, sort of two particle systems. And if we want to think about probes of entanglement in n particle systems, then we need a sort of more general framework. And that framework is what we call quantum games. Okay, so the general idea is the following, and this is why it's called a game. Okay, so I have two players. They're going to be space-like separated. Okay, or maybe I have more players. I have some number of players, but we're going to sort of, okay, they need not be space-like separated, but we should think of them as being unable to communicate with each other during the game. Okay, and they're given a task. Now they can talk before the game, so they can formulate a strategy. But again, we can imagine that they would be able to do this when they're space-like separated, sharing some quantum wave function, and so they're not going to be allowed to talk while the task is being carried out. Okay, and then there's a referee who's going to give them a specific instance of the task and evaluate whether they did it correctly. And the nature of the task is going to be such that classically, at best, for a given instance of the task, they can successfully perform it with some probability p that's going to be less than 1. Okay, but if the players share some entangled quantum state, they can win Okay, they can succeed at this task with some probability that you can show is bigger than p. Okay. And in the examples today, in fact, with this quantum state, you can accomplish the task 100% of the time. And this is often, or this was, in the first papers about this subject, they referred to it as quantum pseudo-telepathy. Okay. And so this, allows one to think about experimental tests for quantum entanglement, kind of Bell inequality-like tests on larger, in a more general framework. And we'll see how to get them to larger systems. So let me begin with the example, which is going to be kind of the foundation of what I'm going to talk about in this talk. And this example is called the parity game. It was first discussed by Merman quite a long time ago, and the version that kind of the language I'm going to use today is courtesy of this paper from 2005. Okay. So the task is as follows. So in this game, we're going to have 3 players, okay, Alice, Bob, and Cynthia. And the referee at the start of the game is going to give each of these players a binary number, so either 0 or 1. But these numbers are going to satisfy the condition that their sum is even. Okay, so that's this sum, AJ is 0, modulo 2. Now, in order to win the game, each of these players has to give the referee a binary number. We'll call those B1, B2, and B3, okay? Such that the sum of these Bs is an even number, or 0 modulo 2, if A is divisible by 4, and an odd number, so 1 modulo 2, if A is only divisible by 2, but not 4. Okay, so that's what this formula here is. Okay. Now, classically, 3/4 of the time, if you just sort of look at the possibilities for what these 3 A's could be, of course, they have to add up to an even number. Okay. So either the referee can give them all 0, or the referee can give exactly one of the 3 of them 0. And obviously, there's more ways to do the second than the first. And so if the distribution of A's is, kind of drawn at random, then 3/4 of the time, they will be right if B1 plus B2 plus B3 is 1. And so, Alice could always give the referee 1, and Bob and Cynthia could always give the referee 0, and they'll win 3/4 of the time, on average. But if they share a particular quantum entangled state, which is this one here, the GHZ state, so a linear combination of all up plus all down, in fact, they can win 100% of the time. So what's the how do they do this? What's the strategy? Okay. Well, basically, each of them applies, takes their qubit and applies the square root of the poly Z operator. Okay, this is a gate known as the S gate to their state. And so after this step, okay, they have, all up and all down, but there's a relative phase here, which is going to be -1 if, this sum over the A's is, not divisible by 4, and it's going to be a +1 if the sum over the A's is divisible by 4. Okay. And so now and then basically they just have to rotate back from an X basis to a B basis to a Z basis, and then they each measure their qubit in the Z basis and return that to the referee. And then they're guaranteed to win 100% of the time. Okay. So, all right. So that's kind of the little algorithm that does the game. And I just want to emphasize, why does it work? Well, basically what's going on here is that we're exploiting the particular entanglement properties of this state, right? This is, it has an all up piece and an all down piece. So it has the superposition, but it also has the feature that, basically once you, like whatever these guys hit, right, they all hit the same thing. Okay. So it's kind of got this, it's the fact that, either everyone's up or everyone's down. So we have this kind of all-to-all entanglement that's being exploited in this strategy. All right. And okay, so that's an example of a quantum game, a kind of generalized Bell test, which, uses a slightly different entanglement structure than the standard Bell test, which are looking for the entanglement of a spin singlet. Okay. And so what I want to tell you about in this talk is two things, addressing the following two questions. So the first question is, maybe we would like to design a game that can give a quantum advantage, when we have the entanglement of some specific quantum many-body state. And so, you might think of this as something you could use to test whether you've successfully, for example, created the Toric code. And so, target a specific quantum state that happens to be a many-body state. The second question that you might ask is, can I design a game that is not so picky about the specific state, but rather only cares that I have the right entanglement properties to be in some quantum phase, right? And this is where you can kind of think about these ideas if we know that, there's sort of universal properties of entanglement of many kinds of ground states, and one would like to be able to target that. Okay, and so the first one I will tell you about in the context of the Toric code. The second one, as we will see, doesn't work so well for the Toric code, but we can do it for the Ising model. All right, so our first step is we need some kind of quantum game that can be, played with some arbitrary number of players. And so a convenient feature of this parity game is that it has a very obvious generalization from one player to any number of players. Okay, and the game is exactly the same. So it's step one. So now we have, some number of players, 1 through n. We've extended the alphabet to contain an arbitrary number of n of letters ending at z. Okay, and at step one, the referee gives each of these players a number, which can be either 0, 1, right? Again, with the promise that their sum is even. And the task that these players have is to return, they each return to the referee a binary number, right? B1 through Bn, such that the sum of all of these binary numbers is exactly half of the sum of the A's modulo 2, right? So it's, odd if A is, even but not divisible by 4, and even if A is divisible by 4. And so, first let's ask what's the best they can do, right? And again, for a fixed n, this constraint that the sum over the A's is even means that, the guessing, it's, slightly more likely for a given n that the answer will be either even or odd. Okay, but as n gets bigger, your kind of classical probability gravitates closer and closer to a half. Okay, so this is kind of the classical probability that you guess just by counting the number of ways to get divisible by 2 versus divisible by 4 for the A's. On the other hand, if you share a specific quantum state, namely the n-qubit GHZ state, so linear combination of everybody up plus everybody down with a relative plus sign, okay, then you can, again, play this game where everybody measures essentially the square root of poly z on their qubit, okay? And that returns a, this same kind of wave function, but now with a relative minus sign, okay? If and only if this sum of the A's, divided by 2 is an odd number, okay? And then you simply do a basis rotation to move this minus sign into some information that you can get, out by a measurement of just in the z basis, and then that tells these guys what to return. Okay. And so, in other words, this 3-player parity game has a very obvious generalization to n players, which you could imagine trying to exploit. Let me just mention. So now, okay, so suppose that you wanted to target a state other than this GHZ state. Can you do that? Yes. So, one thing that you can certainly do is change this from a 2-state system to a Q-state system, right? And there's a version of this game, which you could call, instead of the parity or modulo 2 game, the modulo M, I guess, Q game. So that's a straightforward generalization. I won't talk about that today. But what I do want to talk about is, can we generalize this to other quantum states? And the answer is yes. And let me specifically talk about the ground state of the Toric code. Okay, so let me take a minute to familiarize you with the Toric code for those of you who maybe haven't seen it. So the Toric code, as a physicist, you can say this is just a Hamiltonian that has 2 kinds of terms, okay? One kind of term is a product of poly x's on the 4 spins around the edge of a plaquette. The other term is the product of poly z's around the 4 edges that enter a vertex, okay? And the convenient thing about the terms in this Hamiltonian is that they all commute, so you can solve exactly for all of the states in this system, okay? And in particular, we can create the ground state by doing the following things. So let's take a state in which all of the spins are up in the z basis. That certainly satisfies the vertex constraint. And now we can simply project that state. So by taking a product over all plaquettes of 1 plus BP, which is this product of 4 sigma x's, and we can basically project this state into the ground state subspace of this model. Okay. And so what does that look like? Okay, we start with the state where all spins are up. We now apply sigma x on the 4 spins around a plaquette. We make a little loop. Okay. We apply it around another plaquette. We make a bigger loop, and so on. Okay. And all of these loops, sorry, we have to do the animations again. All of these loops appear with a relative coefficient of 1. Okay. And so the ground state is just an equal amplitude superposition over a whole bunch of, loops where each loop has, spin downs on a loop, and they all appear with a coefficient of +1. Now, okay, why is the Toric code, sort of interesting for quantum information? Well, it has to do with the fact that the ground state manifold in general, if you, for example, use periodic boundary conditions or other boundary conditions where the topology of the manifold is non-trivial, it has a ground state degeneracy. So let me talk about the torus. Okay, so on the torus, there are some quantities that are sort of conserved under this Hamiltonian, but are not generated by products of terms in the Hamiltonian. Okay, so for example, and so I'm going to call these Wilson lines just because you can think of the Toric code as a Z2 gauge theory, and in that language, these are Wilson and Polyakov line operators. But one of the things that I can do is I can count the number of red edges that are crossed, modulo 2 by this dotted blue line, okay? And you can see that this number of edges is not changed by applying any number of plaquette operators, because obviously on a plaquette, there's always an even number of edges. And so you're never going to change this number modulo 2, right? Similarly, I can look at the, right. And so the ground state that I just told you about, which comes from projecting onto the ground state space when all of these spins are up, well, that has an even number, obviously, of red edges, because we created it from a state where there were no red edges, both in the horizontal and vertical directions. Okay. Now there's, but, right. And so this is, sort of a state we'll call 0, 0. Okay. But there are other states, and I'll come back to them in a minute. Now, on the other hand, right. So there's another thing that I can do, okay, is I could actually act with the product of sigma x along some vertical line here, okay? And this is going to flip all spins along some, non-contractible line. So if you kind of look at this dashed red line going around the torus like that, think of flipping all of the spins along there, okay? Now, obviously, and so you can check, very easily, this commutes with all of the terms in the Hamiltonian. We still have a ground state, but obviously it's changed the number of edges that are red that cross this blue loop modulo 2 from plus, from an even to an odd number, right? Okay. And so this creates a state that we call 1, 0, okay? And there's other operators similarly in the other direction, right? I could flip all spins along, this red line here, and that would change the product of poly z's along this line here, okay? And so in total, we have 4 different ground states on the torus. Okay, good. So, but one thing that's sort of important to appreciate is, with these dashed blue lines, right, you can see that, no matter what part of the ground state I'm in, right, it can't matter, okay, where this blue line, how this blue line goes through the system. It's allowed to wiggle. I can move it around, okay, but it just has to wrap around the torus, in this direction. And the answer will always be, -1, or +1, depending on what state you're in, but it can't depend on the trajectory of this blue loop, okay? So in particular, what I'm going to use is the fact that the blue loop could be here, or along any vertical direction, and it doesn't matter. Okay. All right. So we can use this state to play basically a version of the n-player parity game as follows. So what we're going to do is we're going to assign to each player, or you can think of them as teams of players, all of the spins along one of these vertical lines, right? So I have some number of players, and they can measure product of sigma z along some of these lines, right? And then we're going to have one group of players, or one player, who's allowed to measure product of sigma x along a line in the perpendicular direction. Okay. Now, so now, and obviously it's kind of, I've picked a particular geometry. In this geometry, I'm going to give these players the ground state that I've called 0, 0, plus the ground state that I've called 0, 1. Okay. And so, we can, right? So 0, 0, right, is this one, and oops, I don't think I have it here. Right. So, and 0, 1 is the one where I've applied no, I think right. So where I've applied one of these Wilson line operators. Okay. So now what's good? So we're basically going to do exactly the same thing. Okay. But I just want to say 0, 0 here is like, represents this particular ground state of all of the qubits in the system. Okay. And at step one, okay, each team is going to apply their operator, which measures, the product of z's along this non-contractible loop or not. So if they're given an a that's 1, they're going to apply that operator and take the square root. And if they're given an a that's 0, they're not going to do anything. Okay. And now what that's going to do is, again, this 0 1 state is the state where that product is odd. Okay. And so what that's going to do is change this plus sign to a relative minus sign. Okay. And that relative minus sign is going to be picked up by this horizontal team, which is going to measure the eigenvalue of the product of poly X along this horizontal line. Okay. And so this is the basic idea. Note that unlike with the GHG state, there's sort of 2 ways that you can play, right? I can have, the situation that I described where I have teams with vertical kinds of qubits and then 1 horizontal team, right, which is going to measure product of X's. I could also, play with teams with, vertical products of Z's, horizontal products of Z's and a vertical product of X. And in fact, you can kind of do these both at the same time. Okay. So there's no, and that's because, the vertical game, basically this horizontal observer of the vertical game, this red line is the product of X's, doesn't interfere with the team that's sort of measuring the product of Z's over here. Okay. So you can do them both simultaneously. All right. And so, basically what I've shown you is, this kind of all-to-all entanglement of the GHZ state has a sort of, has an analog, if you will, in general in these Hamiltonians of commuting Pauli projectors. Basically because, in the ground state of such a Hamiltonian, there will be many operators typically, right? So, for example, all of these vertical line operators that are all effectively measuring the same thing. So along any line that I measure, right, if I measure product of sigma z along any line, it's always going to give me the same answer, +1 or -1. Okay. And so, really it's this fact, it's these perfect correlations of the measurement outcomes of certain operators in this, what we call stabilizer Hamiltonian, so product of commuting Pauli projectors, that allows us to, define sort of teams or groups of, spins to assign to each player, and play a variant of the parity game and win with probability 100%. Okay, so you could adapt this for many other Hamiltonians, for example, an X cube Hamiltonian, and the only sort of thing that changes is really the geometry of the teams will depend on the nature of the Hamiltonian and the nature of the ground state. Okay, but if you have created a perfect, for example, ground state of one of these stabilizer Hamiltonians, then you can, sort of write down some kind of quantum many-body game, which would be a test of, kind of your ability to make, for example, superpositions of these ground states and have the right kind of entanglement structure there. Okay. Now that's, I think interesting, but it's a very high bar. And so let me turn to the second question, which is, can we actually design games that give a quantum advantage, not so much for a specific state, but rather when our system is in some specific phase of matter. Okay. And so I'll come back to the surface code, but let me begin by talking about the Ising model. Okay, so I talked about this n-player parity game, and let me rephrase that in the context of the quantum Ising model. Okay, so here's the Hamiltonian for the quantum Ising model. Most generally, we're going to talk about a one-dimensional Ising model, although that's not super important. Okay, but so, it has a ferromagnetic term, it has a transverse field term, and it has a longitudinal field. And for us, what we're going to care about, or the way we're going to think about the system is in terms of its ground state in a finite system of some number n of spins, which, we're going to allow to be large. Okay. So, obviously, if I turn off these fields, okay, the ground state is a state in which, all of the spins are aligned with their neighbor. And when these guys are exactly zero, there's actually a ground state degeneracy. And one of those ground states is exactly this GHZ state. And I should say, if you turn on a very tiny transverse field, but leave H off, then, you would favor exactly this guy as the exact ground state. Obviously, if you turn on a tiny H, you favor, one direction, either up or down. Okay. Good. On the other hand, if I turn off the ferromagnetic coupling and I say only have this transverse field, okay, then everything is aligned just in the X direction. This is what we call the paramagnetic phase. Okay, right. And yeah, right. Obviously, if I turn off this transverse field, right, then the ground state is now unique, and it's, for example, it's basically everyone's aligned, and the direction that they're aligned in just depends on the sign of H. Okay. All right. And so the phase diagram of this model looks like the following, right? So basically, anytime I have this longitudinal field on, I have broken a symmetry. And in fact, there's no phase transition, okay? And also no, correspondingly, no ground state degeneracy. There was no symmetry, and so there's no spontaneous symmetry breaking. However, if I turn off this longitudinal field, I do have a symmetry, right? So that the model is symmetric under flipping all of the spins. And then I have two phases. One is a ferromagnetic phase, okay? And this phase has spontaneous symmetry breaking. And you should think of this phase as being, whoopsie-daisy, as being, kind of ground states in this phase are sort of adiabatically connected to this many-body GHZ state, all up plus all down, okay? That's why I'm picking out this particular one as the ground state, okay? And then when gamma gets bigger than J, we have a transition to what we call a paramagnetic phase. And here the ground states are adiabatically connected to a product state. Okay, right. Okay, and here's just the words that I just said. Okay. Okay. So then you can ask, well, suppose that I play this n-player parity game. Does that work throughout the ferromagnetic regime? And basically, what you can show, and I won't go through the details, but I think it's sort of not too surprising, is that in order to win the n-player parity game, what you care about is the overlap of your specific state. So here we're imagining that psi naught is, the ground state of the quantum Ising model at some parameter value. And what we care about is the overlap of that state with the n-particle GHZ state, right? Minus the overlap of that state with what I'll call GHZ twiddle, which is basically this n-particle GHZ state with the plus turned to a minus. So basically what you find is that, if you start with the GHZ state, you win with 100% probability. If you start with the GHZ state, but with the plus exchange for a minus, you lose 100% of the time. And with anything else, basically, you're 50-50. Okay. And so this is what we find. Fortunately, and this is kind of the reason that it's nice to look at the 1D Ising model, that you can solve exactly for these ground states, okay? And so there's an exact formula that you can use to calculate these overlaps in terms of this parameter G, which is just gamma over J, okay? And this product over K's, there's a bunch of them that are basically, for those of you who are familiar, these are the allowed momenta of the Jordan-Wigner fermions, okay? And so this is our quantum probability of winning. Unfortunately, this quantum advantage falls off really rapidly as the number of qubits gets large. And so, this would be no good for any kind of empirical, test of being in some particular phase. Okay. However, it's, maybe for smaller systems, it's actually, kind of interesting to note that when you, okay, so first of all, this formula, works exactly, and also that when you look at relatively small systems where, Vera could do some numerics, you actually do get a little bit of quantum advantage, even going past this threshold where the phase transition occurs. So this here is the optimal classical strategy. I believe this was for 6 qubits. And this is the, kind of the quantum probability of winning for the exact ground state at different points in the phase diagram. And the other thing to notice is that you can also ask what happens when I turn on this longitudinal field and break the symmetry. And here, in fact, you lose your quantum advantage completely throughout the phase diagram. Okay. So the moral of the story is, provided that you have the symmetry of the Ising model, okay, and you're in this situation, right? So it's really the symmetry that, kind of gives us some entanglement in the ferromagnetic phase. We do get some quantum advantage, and perhaps somewhat surprisingly, we even see some quantum advantage, past the phase transition, but that quantum advantage is very, very tiny, right? Because it's falling off basically exponentially quickly in n. And so the question is, but we know that there is some kind of characteristic long-range entanglement in the ground state of the Ising model, on a finite size system. And so how might we access that long-range entanglement, kind of through some kind of quantum game? And so one way to do this, and there's also, a paper about a similar question for one-dimensional cluster states or symmetry-protected topological phases, which is here. But the basic, or a basic way to get around this is to not assign every spin to a player, but to give the players only some subset of the spins. And if you choose those at random, they are typically well separated. Okay. And in particular, okay, so by keeping P finite, we'll see that we avoid this exponential and n suppression of the fidelity. And, kind of intuitively, by keeping these spins that we're playing with far apart, on average, we ensure that the probability of winning basically depends only on the long-range correlations. In other words, it depends only on the features that are sort of characteristic of the phase. Okay. Right. And so you can evaluate, okay, so there's, basically the strategy here is always the same. And you can evaluate the probability of winning in a given state, given that we're picking out some number, P of qubits with which we play, okay? And you can reduce the calculation of the quantum advantage to calculating the expectation value of a particular operator B, okay? Which is basically, what is the probability that all of these guys are up? What's the probability that they're all down? And then this here is picking out, whether we have all up plus all down or all up minus all down. So we're going to measure that guy, okay? And you can show, again, basically using the exact solution of the 1D quantum Ising model, that when the players are well separated, so if we pick all of these spins and they're far apart, such that these sort of probabilities of both spins being up are simply given by the long-range order parameter, which is m, that the quantum advantage satisfies a formula that looks like this. Okay, and so in particular, in this limit that the spins are all very far apart, unsurprisingly, the quantum advantage depends only on the magnetization of the state. But I want to emphasize that this is under the assumption that the ground state is invariant under the Ising symmetry. Okay, we're using that. Without that, we're not guaranteed entanglement. Okay, And so this is, what this looks like as a function of the number of players that I pick for this phase diagram, okay, for a very large number of spins, okay. So here we're assuming that n is very large, but we're picking some number p, 3, 6, 9, 12 of spins and just sort of calculating what would our quantum advantage look like, right? And you can see that basically you get a finite quantum advantage, which does not die as n grows, for almost all of the ferromagnetic regime. Now, it turns out that with this particular algorithm, it actually disappears a little bit before the critical point. Now, it doesn't get you quite all the way to the critical point. If you want to do that, you can actually bias the distribution of possible values that the referee gives to the players, and then you can get to the critical point. Okay. So this is sort of the, very basic demonstration that yes, we have this game, which originally, was supposed to be played with a GHZ state. But if we, sort of coarse grain the rules of the game, if you will, in fact, we can see this quantum entanglement from the combination of symmetry of the ground state, which ensures that we have this, superposition of psi and, psi with all spins flipped. Okay, that's kind of what's generating the entanglement. So we have this, combination of symmetry, which generates this entanglement, as well as these classical correlations. Okay, and the last thing I want to sort of maybe touch on before I take questions is, you might have wanted to similarly be able to sort of coarse grain this toric code game to be able to, give some kind of quantum advantage anytime I had a ground state, of a pure system, which was not, the ground state of the toric code Hamiltonian, but rather a ground state in the same phase. Okay, so what do I mean by that? Well, here's the original, here's a general Hamiltonian that I could write down. Okay, so this is in the top line, it's the original toric code, right? Here's my plaquette term and here's my vertex term. And then in the bottom line, I've just added a couple of, basically background magnetic fields, one in the x direction and one in the z direction. So the field in the x direction obviously commutes with these plaquette terms, but it creates vertex violations, okay? So it competes with this term. And the field in the z direction obviously commutes with the vertex term, but it creates violations, pairs of violations of the plaquette term. So there's a competition here, okay? And the phase diagram of this model is very well known. It dates back to the classic work by Fradkin and Schenker on Z2 gauge theories, okay? And, basically, there's values of, we'll set epsilon p and epsilon s both to 1, okay? And then there's values of these fields where you cross a phase transition from the toric code phase to a trivial phase, okay? Trivial phase meaning that the ground state is adiabatically connected to a product state. Now, so we are interested in, asking what can we do with ground states that are in this toric code phase. But there's an important difference here relative to the Ising case, okay? So in the Ising, in the ground state of the transverse field Ising model, in the ferromagnetic phase, there are long-range correlations and, kind of long-range classical correlations, but those were sort of part of what we leveraged to actually gain this quantum entanglement, quantum advantage in our game. In the ground state of the toric code, life is a little bit different, okay? Which is to say the difference between being in the ground state in the toric code phase and the ground state in this trivial phase, in terms of the observables that we're using here, are whether these lines of spins, whether they're satisfy so their expectation value, in the Ising model, right, we had these sort of long-range correlations that were finite in the limit that the system got very large. In this case, basically, the distinction is these loop order parameters fall off either with the length of the loop or the area enclosed by the loop, okay? And so here in particular, when we're in this toric code phase, what we expect is that these line operators have expectation values that fall off exponentially in the length of the system in this other direction, right? And this guy has an expectation value that falls off exponentially in the length of the system in the x direction. Okay. And so, unfortunately, what we would have liked to do to play our game, right, would be, apply some bunch of these guys, apply some bunch of these guys. But unfortunately, these order, the kind of order parameters for the observables that we would like fall off exponentially in the system size. And so in the toric code, this parity game, although it works well specifically for the toric code Hamiltonian, sum of commuting projectors of Pauli's, where this kind of parity game can always work in some fashion. So here, I can do this for any n, even if we coarse grain basically anywhere besides this toric code point in the phase, we're going to lose our quantum advantage exponentially quickly in n. Okay. And so I think the underlying reason for this is that in the Ising phase, the entanglement, the all-to-all entanglement that we are exploiting in this game is a feature of the entire ferromagnetic phase. It's related to these long-range correlations, again, together with the fact that we have this symmetry. For the toric code, the reason that we can't generalize the game to an entire phase is that these all-to-all correlations are kind of specific to the toric code point and not in fact capturing, so the kind of entanglement that we're using to play this game is not, sort of capturing maybe the universal entanglement of the ground states of the toric code. Good. And so, maybe just to recap the main points, I think, these quantum games or generalized Bell's inequalities are an entertaining probe of entanglement that you could imagine, implementing in an experiment. And specifically, I talked about this parity game, which exploits a kind of entanglement that happens in situations where, you have sort of perfectly correlated measurements over many players. And, I show that you can do this with GHZ states, with the toric code ground state. And as I said, any kind of, Pauli stabilizer Hamiltonian admits a version of this game. And I also showed you how it can be adapted specifically for the ground state of an Ising model to yield advantage throughout the entire Ising ferromagnetic phase. Whereas, basically the kind of correlations that we're leveraging are not characteristic of the entire toric code phase. And so there, it doesn't, we don't know how to extend it to cover the entire, kind of region where we expect there's some kind of interesting quantum entanglement there. All right, and let me end there and take any questions.
All right. Thank you, Fiona, very much for a very nice talk. And now the session is open for questions. If you have a question for Fiona, please feel free to unmute yourself or raise your hand if you prefer, or you can type your question in the chat. So I will start with a very simple question or practical question. So have you tried or thought about actually implementing this with, in some of the quantum infrastructures out there?
I mean, yes, we've talked a little bit to a few people. I think, I mean, we have not yet convinced, let me put it this way, we have not yet convinced someone to do it. And although I still harbor some hope of doing that, but I think, one of the responses that we got was, well, there's a method called, sort of shadow tomography that allows, for example, measures of entanglement. And, so there are other ways to measure entanglement. And I think, the experimentalists, who are under a lot of pressure to, produce results that are sure to get a lot of attention, feel like maybe demonstrating another way of measuring entanglement won't get enough attention. But I think that there is, I also am not, I think that the kind of fidelity that actually, is being that we're testing, the fidelity between these sort of superpositions of different ground states is very, very delicate. And so, it's I think it's a pretty high bar to actually find it in these open quantum systems. So, it's not clear to me what would happen if you tried to implement it on, on one of these machines. I'd be curious to find out.
All right. Any other questions from the audience? All right. If not, we thank Fiona one more time. Thank you, Fiona. I appreciate you taking the time to be with us. And we stay in touch for another Quantum Matter seminar I think on Thursday. All right. Goodbye, everyone.
All right.
Bye, Fiona. Thank you so much.
You do 2 per week. That's a lot.
No, this is an exceptional week. This is not normal.
Gotcha.
There are people coming through Boston, visiting different universities, and when we can snatch someone to give a talk, we do.
Yeah.
And so sometimes we're lucky. So if you're in town, please, or planning to come to the East Coast, let us know.
Yeah. This year is I'm keeping my travel limited, but probably starting next year it'll be a little bit less. So
all right, maybe I see you at the March meeting then.
Yeah, I will be here. That's good. Take
Bye
care.
bye.